Let's dive into the digital trenches. Today, we're looking at how a new generation of AI is learning to fight one of the internet's oldest and most disruptive threats. You're about to see exactly how it works.
You know that feeling, right? You're trying to stream a show, log into your game, get something done online, and poof, nothing. The service is just gone. You hit refresh, you check your Wi-Fi, but the site just won't load. So what's really happening? Well, a lot of the time, it's no accident.
The culprit is often an invisible, overwhelming force, a distributed denial of service attack, or DDoS for short. As you can see here, you've got one attacker acting like a puppet master for a whole network of compromised computers, a botnet. They point all of them at a single target and just flood it with useless traffic until it completely overloads and shuts down for everyone.
Now, to really get a handle on the solution, we first have to appreciate the scale of the problem. And honestly, the best way to think about it is as a massive digital flood.
So a DDoS attack isn't really a heist. The goal isn't to steal your data. It's more like creating a gigantic, malicious traffic jam on the information superhighway. It's all about overwhelming a server's resources, its brain power, its memory, so that legitimate users, like you and me, just can't get through. It's pure weaponized chaos.
And this isn't a one-trick pony either. Attackers have a few different ways to create this mess. They can go with a volume-based attack, which is basically a tidal wave of junk data. Or they might try a protocol-based attack, which messes with the basic handshake rules that computers use to talk to each other. Then there are application layer attacks, which are kind of like having thousands of bots hitting the refresh button on a website all at once.
All this complexity leads us straight to the heart of the problem, the detection challenge.
So this raises a huge question for the defenders. How in the world do you tell the difference between a real surge of users, say for a big sale, and a malicious flood of bots? It's like trying to find a needle in a haystack, except the haystack is also on fire and moving at the speed of light.
And the hurdles are immense. For one, attackers are constantly changing their tactics. Then there's the sheer volume of data you have to analyze. It's like trying to drink from a fire hose. And you've got to find a balance. If your defenses are too aggressive, you start blocking real people. Too relaxed, and the attack gets through. But the worst part? Zero-day attacks. Brand new methods that have no known signature, making them totally invisible to traditional security.
So how do you fight a threat that's always learning and evolving? Well, you build a defense that can learn too. And that's exactly what researchers have done, by teaching machines to see the patterns that we humans just can't.
To build this smarter defense, researchers didn't just throw some AI at the problem. No, they developed a whole battle plan, a structured framework. It all starts with getting tons of data. Then, they figure out which pieces of that data are the most important. From there, they split it up for training and testing. And finally, they teach the AI what to look for and grade its performance. It's a very deliberate process for building a world-class digital detective.
Let's break that down real quick. First, you gather the evidence, just massive amounts of real-world network traffic. Second, and this is the super important part, you do something called feature selection, which is all about finding the most critical clues. Then, use 80% of that data to teach the AI what an attack looks like, and you save the other 20% for a final exam. Step 4 is the actual training, and Step 5 is seeing if your detective is ready for prime time.
The researchers basically hired two types of detectives for this job. The first is a support vector machine, or SVM. Think of this one as a master analyst. It looks at all the data points and draws the absolute clearest possible line to separate the good guys from the bad guys. The other detective is K-nearest neighbor, or KNN. This one's more of a neighborhood watch. It looks at a new piece of traffic and decides if it's suspicious based on the company it keeps. If all its neighbors look like trouble, it gets flagged.
But here's the thing. The real breakthrough wasn't just using these AIs. It was about making them work smarter, not harder.
And this is the secret sauce right here. In a massive flood of information, most of it is just noise. The game-changing idea is a process called feature selection. It's a way to automatically tell the AI to ignore all that distracting noise and focus only on the few critical clues that scream, "This is an attack." So how did they find those clues? This is the cool part. They looked to nature. Seriously, they used algorithms inspired by how animal groups work together. There's gray wolf optimization, which mimics how wolf packs hunt. There's particle swarm optimization, which models a flock of birds and is surprisingly effective. And there's the SALP swarm algorithm, which is based on sea creatures. It's biomimicry for cybersecurity. How clever is that?
Okay, so we've got this super smart, nature-inspired system. But did it actually work?
Let's get to the results, because this is where it gets really, really good. Right, after all that complex work, gathering data, training AIs, using algorithms inspired by wolves and birds, the big question remains, did the digital detective actually catch the bad guys? The AI's performance was graded using this, a confusion matrix. It's basically a simple scorecard. The top left and bottom right boxes, those are the right answers. The other two boxes are the mistakes. So the goal is simple. Get the numbers in the green boxes as high as possible and the numbers in the red boxes as close to 0 as you can get.
So what was the final grade? An average accuracy of, get this, 99.9%. Yeah, let that sink in for a second. That is astonishingly close to perfect. These models could tell the difference between a normal user and a malicious bot almost flawlessly.
And this chart just drives the point home. One of the new models, the one combining particle swarm optimization with the SVM, achieved a perfect 100% score. Now compare that to older methods like recurrent neural networks, which were struck down around 89%. That isn't just an improvement, that's a massive leap forward.
I mean, even the researchers, who are usually very understated in their papers, couldn't hide how well it worked. They wrote, "The results show that the proposed models achieve high results, 99.9%. In plain English, that means, yeah, this thing works incredibly well."
So what's the big takeaway here? It's that the future of our digital defense isn't about building bigger walls. It's about building smarter detectives. By teaching AI to focus only on the clues that matter, we can create defenses that are faster, way more accurate, and more reliable, making the internet a whole lot safer for all of us.
Look, this research is a huge win for the good guys. It proves we can build these incredibly intelligent, adaptive systems. But it does leave us with one final big question. In the constant cat and mouse game of cybersecurity, can our defenses continue to evolve as fast as the threats they're built to stop?